All right. Yeah. Thanks very much, Avi, for inviting us to give these two talks. So I'm going to be giving the first talk in this two-part series, and Sebastian, who's in the audience, I think, will give the second part tomorrow. So I'm going to be speaking about superpolynomial lower bounds against low-depth circuits. And my aim is to sort of give you a high-level description of the result and maybe some of the background in the area. The proof itself turns out to be quite simple and elementary, and we're quite happy about that. And Sebastian will give you maybe more details of the proof tomorrow, and that should be fun. So this is joint work with Nutan Limay and Sebastian. So let me start with an overall high-level description of the talk. So the result is about a kind of a lower bound for a model of computation. As describing the model of computation itself is not very difficult. It's quite simple and nice to describe. So I can give you the statement of the result without much background. And then I want to kind of motivate the result in a couple of ways. The first motivation is by sort of illustrating the power of the model of computation by describing a nice construction due to Ben-Or. And then I'll give you a little bit more context behind the result and connections to more kind of some important problems in computational complexity theory, specifically the VP versus VNP question, which is sort of the motivating question behind this area. And if I have some time, I'm going to describe some applications for our result, specifically to polynomial identity testing. And if I have lots of time, maybe some high-level proof details. But I really don't expect to spend too much time on the latter two things. So feel free to stop me, ask me questions, slow me down, anything that's unclear. Of course, I know you'll do it, but just to be, to make absolutely sure. Okay, so let's get started. So let me give you the statement of result. So this is a result. This is a result theorem about multivariate polynomials. So throughout, we're working over some field f. Later on, I'll have to assume something about the field, but for now, let's just say we're working with some arbitrary field f, and we're looking at multivariate polynomials and some n variables over this field. And we're going to look at degree d polynomials where d is typically bounded by n. Yeah, and in fact, the results that I'll describe to you, d is actually much smaller than n. So think of d either as a large constant or maybe slowly growing with n, like log n or root n or something. Okay, so what's a multivariate polynomial? Well, by definition, it's a formal linear combination of monomials, right? So this is how a multivariate polynomial is defined. And an expression for a multivariate polynomial of this form is what I'll call a sigma pi formula for the polynomial p. Okay, so this is a sigma pi formula. And the reason for the name is fairly clear, right? It's a sum of product of things, and those things are variables and field constants. So therefore, a sigma pi formula. Okay, and I think of this as just an expression written down on a piece of paper. So the size of this expression or the size of this formula is essentially the number of symbols I need to write down this expression, right? And of course, here, this is just the number of monomials in this polynomial with non-zero coefficient. Right, so that's roughly the size of this expression, give or take a factor of d. Yeah, and this can be as large as the number of monomials of degree d overall, which is something like this binomial coefficient here. And I think of d as much smaller than n, so this is roughly like n to the d or something. So this is as large as it can be. And I'll think of expressions of this size as essentially being trivial, right? Because I can always come up with an expression for a polynomial of this size by just writing it out as a sum of monomials. Okay, so that's this is a sigma pi formula. And the question that we are sort of interested with in this talk is whether we can come up with significantly smaller, more succinct expressions, which are somewhat more complicated. So can we sort of trade off can we trade off in the sense that can we look at more complicated expressions, but which are much smaller than this? Okay. And so if you think about this problem in a sort of bottom-up way, a natural class of expressions to look at are what are called sigma pi sigma formulas, which are what I'll now define. Okay, so what's a sigma pi sigma formula? So it's just a slightly more complicated kind of expression. So instead of looking at sums of products of variables, you look at sums of products of sums of variables and field constants. So in other words, the variables in the previous expression get replaced by linear polynomials in the underlying variable set. Okay, so these are polynomials of degree at most 1. So they could be constants or they could be of degree 1. Okay, so this is what is called a sigma pi sigma formula for obvious reasons. And again, I can think of this as an expression written down on a piece of paper like this, or sometimes it's more advantageous to sort of think of this as this picture. Okay, so this picture essentially represents the same thing as this expression here. This plus at the top of the picture represents the outermost sum. The products sort of feeding into the plus represent the individual summands, and the pluses feeding into those products represent the linear functions, and so on. Okay, so this is a kind of just a different way of writing the same thing. But the advantage here is that you can define some nice combinatorial properties of this expression. So for instance, you can talk about the depth of this formula, which is essentially the length of the longest directed path in this rooted directed tree. So this is a depth 3 formula. It can also be seen as the nesting depth of this expression. So it's a sum of products of sums, so depth 3. It's a depth 3 formula. And again, the size of this expression is just the number of symbols you need to write it down, or equivalently, more graph theoretically, it's sort of roughly the number of edges or wires in this graph. Okay, so that's a sigma pi sigma formula. All right, so what's the question again? So the question is, can we find like succinct sigma pi sigma formulas for the polynomials we're interested in, right? And the answer to this question, it actually depends, of course, on the polynomials that you're looking at. So it turns out that for a random polynomial or a generic polynomial suitably defined, the answer is no. Okay, so there is, in fact, not just sigma pi sigma formulas, but much more general expressions. You can say that a random polynomial has no general expressions of size much better than trivial. Okay, so you can't really do better than just write down a polynomial as a sum of monomials. So that's the best you can do for a general polynomial, for a generic polynomial. But in this case, in this result, we're not interested in what happens to generic polynomials, but rather explicit polynomials that we are actually interested in. Okay, so I have to be a little bit careful in this term. When I use this term explicit, it's not really well defined. I'll give you one way of defining it later. But for now, just think of it as explicit just means a polynomial that you know, that comes up in your daily mathematical life, a polynomial that has a name, a polynomial that you can write down. Any reasonable definition of the word explicit will do. Okay, so given such an explicit polynomial, can you find a small sigma pi sigma expression for it? That's the question. Yeah, and for many well-defined, nice families of explicit polynomials, we believe that the answer is no. Okay, and I'll give you examples of such polynomials in the coming slides. But for many explicit polynomials, we believe that the answer is no. And so the question is, can we prove this? Okay, so can we prove that certain well-defined explicit polynomials that we have written down in front of us, can we show that they have no small sigma pi sigma expressions? Okay, so ideally, we'd like to show that they don't have better sigma pi sigma formulas than sigma pi formulas, just like the generic case. But failing that, can we at least prove something non-trivial? Okay, and what is non-trivial? Well, a polynomial that really depends on all the n variables, of course, requires at least n symbols to write down. So n is trivial, and so non-trivial is something that's significantly more than n. Okay, so significantly more than n. So as a function of n, it's like a super polynomially growing function of n. Okay, so that's the question. Yeah, and the main result here is exactly a solution to this problem. Okay, so this is the result. So we work over fields of characteristic 0. So over any field of characteristic 0, we show that there are explicit sequences of polynomials that have no sigma pi sigma formulas of size polynomial. Okay, so that's the statement of the theorem, and I can be quite explicit about my explicit polynomials. So here are some examples. So for instance, we can consider the n by n determinant. Right, so take an n by n matrix, a little n by little n matrix, and we think of the entries of this matrix as indeterminates. So that's little n square, capital N many indeterminates, so capital N is little n square. And the determinant is a polynomial of degree little n in these n squared indeterminates. Right, it's this polynomial here, well-known polynomial. Okay, and in particular, what our result implies is that if you look at this infinite sequence of polynomials, and you look at the smallest sigma pi sigma formula for each value of little n, the size of such a formula grows faster than any polynomial in little n. Okay, so that's what our result implies. Yeah, and we also prove the same result for the similarly defined permanent polynomial. So in case you haven't seen this polynomial before, it's exactly the same as the determinant. So it has exactly the same monomials, only the coefficients are all 1. So there's no plus or minus 1. The sign term does not exist. So all the coefficients are 1 for the monomials that appear. Okay, so that's a permanent polynomial. And again, we get the same result for the permanent polynomial. Okay. One final explicit sequence of polynomials that are very interesting for us are the iterated matrix multiplication polynomials. So what are these polynomials? So I'll spend a couple of minutes here because these are important in our result. So imagine that we have a bunch of n by n matrices, right? So around, I guess, d minus 2 n by n matrices. And we also have a row vector and a column vector, x1 and xt. So the product of all these matrices is going to be a scalar, right? And that scalar is going to be a polynomial in the entries of these matrices. And whatever the entries of these matrices are, we think of those as indeterminates, and the scalar is a polynomial in those entries. And whatever that polynomial is the iterated matrix multiplication polynomial, abbreviated IMM with these parameters. Yeah, and again, this is a polynomial in a certain number of variables, capital N, something like d times n squared. And what we show again is that for d being a suitable function of n, so for a suitable degree, this polynomial does not have sigma pi sigma formulas of polynomial size. Okay, so that's the statement of the result. This is possibly a good time to pause and ask if there are any questions. Anything?
They're very clear so far.
Okay, perfect. All right, so let me carry on. Yeah, I should say that our result is not specific to sigma pi sigma formulas. So once you have sigma pi sigma formulas, you can ask about sigma pi sigma pi, sigma pi sigma pi sigma. So you can look at more complicated kinds of formulas. And the result also applies to all these families of expressions, as long as the depth of these expressions, right? So which is essentially the number of symbols that defines the name here. So sigma pi is depth 4 and so on. As long as the depth of these expressions is a constant independent of the number of variables and the degree of the polynomials. Okay, so that's the setting in which our result works.
Second, what about the circuits?
Okay, so great. In the setting of, so we'll talk about circuits in a little bit, but to answer your question, in the setting of constant depth, formulas and circuits are roughly the same. So you can go from one to the other with only a polynomial blow up. So it also applies to circuits.
Okay, one more question. So in the Boolean case, our techniques actually work degree up to like the law of log n over log n or something.
That's right. So the Boolean case, we get up to degree, depth log n over log n, but here we are not able to go that far. So actually we go up to depth something like log the degree. And the degree itself is constrained to be like log n. So it's really bad as a function of n. Yeah. Okay, great. Yeah, thanks for these questions. Okay, so now I want to kind of motivate this model a little bit more with this construction that I told you about of Ben-Or. So what this construction sort of illustrates is that this model can actually be surprising and counterintuitively powerful in certain settings. So I want to illustrate that for you. So this is just a construction of sigma pi sigma formulas for a certain interesting family of polynomials. So what are these polynomials? These are the so-called elementary symmetric polynomials. Okay, so just to recall, the elementary symmetric polynomial of degree d in n variables is the following polynomial. So you have n variables x1 through xn, and the elementary symmetric polynomial of degree d just sums over all subsets of these n variables of size d, the product of the variables in the subset. Right, so for every subset of size d, you have the product of all the variables in that subset. That's a monomial of degree d, and you sum over all monomials, all such monomials of degree d. Right. So this is a polynomial which has, of course, a sigma pi formula with n choose d monomials. So that's roughly the size of sigma pi formula defining it. And this is pretty close to trivial. So if you think of d as much smaller than n, this is roughly n to the d. So this is kind of like trivial, right? And it's also a nice kind of irreducible polynomial. So a priori, there is no reason to believe that this has a small sigma pi sigma formula smaller than this. But nevertheless, it does. So this is this kind of construction of Ben-Or. So what it says is that for any d, this polynomial has sigma pi sigma formulas of size n squared. Okay, so that's kind of surprising. And let's see why. So I'll give you this entire construction, hopefully, in this slide. And the basic idea, the very simple idea that this construction uses is a kind of a familiar fact from basic algebra, which is that if you have a quadratic polynomial, for instance, right, you can find the coefficients of the quadratic polynomial by evaluating at any 3 distinct points and then taking a suitable linear combination of these evaluations, right? And more generally, if you have, so this is a quadratic univariate polynomial, just to be clear. And similarly, if you have a polynomial of degree, a univariate polynomial of degree n, you can always obtain the coefficients of this polynomial by evaluating this polynomial at n+1 points and taking a suitable linear combination, right? So this basic fact is what we'll use, and in a very simple way. Okay, so let's proceed with the construction. So take the elementary symmetric polynomial of degree d. So the first trick is to not just consider this single elementary symmetric polynomial that we're interested in, but really all elementary symmetric polynomials together, right? For degrees going from 0 all the way through n. Okay, so more precisely, we consider the following generating function. So some j going from 0 to n, the elementary symmetric polynomial of degree j times an auxiliary variable t raised to the power j. Okay, so this is a generating function for the elementary symmetric polynomials. And it's fairly simple to see that this generating function has a very nice simple form. It's just the product I going from 1 to n, 1 plus t times xi. Okay, and why is this? Well, this can be easily proved by inspection. Just expanding out this term on the right-hand side, you see that the coefficient of t to the j is exactly all those monomials in the x variables that contain exactly j distinct variables, which is exactly the elementary symmetric polynomial of degree j. Okay, so this has this very nice expression, and I'll think of this as a univariate polynomial in T, suppressing the dependence on x1 through xn. Okay, and now the observation is that while the elementary symmetric polynomial doesn't seem to have a small expression, this polynomial q of t definitely does. Here's the small expression, right? So this has a formula of size n. Okay. And now, and furthermore, the polynomial that we're interested in, the elementary symmetric polynomial, is exactly the coefficient of t to the d in this polynomial q of t. Okay, so perfect. We're exactly in the kind of setting where interpolation is useful. We have a univariate polynomial q of t. What we want is the coefficient of t to the d. So what are we going to do? We're just going to evaluate this polynomial at a bunch of points. This is a polynomial of degree n, so we'll evaluate it at n+1 distinct points and take a suitable linear combination, and that will be the coefficient of t to the d. Okay, and that's exactly what we do. That's the construction, right? So you evaluate this q at n+1 distinct points from the field. So we need the field to have size at least n+1, but this is a minor criterion. And then taking a suitable linear combination, we get the elementary symmetric polynomial of degree t. Okay, so this is the construction. And let me just write down the polynomial we get on the next slide. So this is the polynomial. Okay, so we took the polynomial q, we evaluated it at n+1 distinct points, took a linear combination, and that gives us the elementary symmetric polynomial of degree. Any questions about this? Okay.
I have a question.
Yes.
So in your definition of arithmetic circuits, are you allowed to evaluate your polynomial in fields that are not the underlying field, like passing to algebraic closure or something like that?
Yeah, so well, in the way we defined it, we don't really, yeah, our field, so we have some sort of base field, and we allow constants from that base field and no more. But typically, when we look at algebraic circuits, we usually sort of just look at algebraic circuits over an algebraically closed field. So, you know, if you can come up with an algebraic circuit for your polynomial over the complex numbers, that's typically the setting we're interested in. Yeah.
Okay.
Anyway, it was not used here, right? The use of the elementary symmetric polynomials as functions of these extra variables xi.
No. The only reason I'm asking is because there's a condition that the field is large, but if you're over algebraic closed field, it is large. Yeah, right?
That's true. But often, I mean, the arithmetic complexity theory is interested in fields of, infinite fields in particular, let's say for error correcting codes applications, stuff like that. It's interesting for all fields, and we try to prove it for whatever fields it's
Right. Yeah, so it should be stated that this field being size in this large in this construction is actually not just an artifact of the construction. So over F2, for instance, you can show formally that there is no small sigma pi sigma formula for the elementary symmetric polynomial. So in some sense, some condition on the field is necessary. And this construction simply tells you that as long as the field is large enough, it's fine. And typically in this world, we think of the field as however large we want it to be.
You probably know it from, those who know the Boolean complexity theory results for constant depth circuits. The fact that parity or majority cannot be computed by Boolean, or Boolean can be working on a small finite field. yeah, they imply that this condition is necessary.
That's right. Right. Great. Yeah. So perfect. So this is the sigma pi sigma formula that we constructed. And if you look at the size of this formula, right? So you have a sum of n, roughly n terms, each of which have size roughly n each. So you have a formula of size n square. And this is what we claimed. Okay, so that's the construction of Beno. So it's a really beautiful construction, completely counterintuitive. And among the many counterintuitive features it has, here's one that's really kind of striking in my view. Recall that what we want to compute here is the elementary symmetric polynomial degree d, and you can think of d as any parameter less than or equal to n. So it could, in principle, be much smaller than n. But nevertheless, if you look at the individual terms in this sum, each of them computes a polynomial of degree n. Right. So even though maybe you want to compute a polynomial of degree log n in the end, you want to kind of express this polynomial of degree log n, but nevertheless, you can compute all these intermediate terms of degree much more than log n, of degree up to n. And somehow when you take this linear combination, all those higher degree terms kind of cancel out. And what you're left with is exactly what you want, this low degree polynomial. Okay, so these intermediate terms have degree much larger than n. Okay, and it turns out that this is not just an artifact of this construction. This is actually necessary. Okay, and that's what Avi proved in this beautiful result with Noam Nissan that we'll come back to again and again. So what they showed was that if you look at homogeneous sigma pi sigma formulas, so where you restrict these summands, individual summands also to compute polynomials of degree at most t, then in fact you cannot get expressions for this polynomial of non-trivial size, of size much better than n choose t. Okay, so you really do need this kind of inhomogeneity. All right, so that was just an aside, but the main take-home message from this construction is that this is an interesting kind of family of representations that can do non-trivial things and sometimes unexpected things. Okay, so there are a few other examples of phenomena like this. So we just saw this elementary symmetric polynomial thing, but let's also look at some of the other polynomials that I already defined. So for instance, when one looks at the n by n permanent, the permanent of order n, so recall that this was just the same as the determinant, but without the sign term, right? So the number of monomials that it has is n factorial, which is roughly n to the n. And it's kind of by now a classical fact that it has a sigma pi sigma formula of size something like 2 to the n. Okay, so this is called a Reiser's formula, and it's probably a fairly standard construction that shows up maybe in exercises on inclusion exclusion, for instance. So it's actually a pretty simple application of inclusion exclusion. It doesn't need interpolation or inhomogeneity or things like that, but it's still fairly clever, and 2 to the n is much better than n to the n. So again, this shows a significant improvement. And for a long time, people also wondered about whether there are similar things for the determinant. Okay, and so in this area of work, typically we think of the determinant as much simpler than the permanent for all sorts of reasons. And so it was kind of counterintuitive that we had such a small sigma pi sigma formula for the permanent, but nothing for the determinant. And this was true for a long time until about 5 years ago or so, where there was this beautiful paper of Gupta, Kamath, Kayal, and Saptarishi, who showed that the determinant has sigma pi sigma formulas, not just of size 2 to the n, but of size closer to 2 to the root n, okay? Something like n to the root n. So it's much better than 2 to the n.
Srikanth, this is still true only over characteristic 0, right?
Right, yeah. So yeah, Avi makes a good point. I should mention that.
We don't know this for even large finite fields.
That's right. This construction is also true over characteristic 0. And not over, I mean, it's not known to be true over positive characteristic, right? And another interesting thing about this construction is that it actually combines both the ideas of the previous two constructions. So it kind of uses inclusion exclusion, and it kind of uses interpolation. It combines them in a clever way, and it does this. Yeah, and it also works for other families of polynomials. For instance, for the iterated matrix multiplication polynomial, it gives a non-trivial upper bound of n to the root d. Whereas the number of monomials in this polynomial is like n to the d. Okay, so again, super polynomial improvement. Okay, so all this to say that sigma pi sigma formulas can be smart and clever, can do unexpected things. But as you can see in the latter three examples, we don't always have polynomial-sized sigma pi sigma formulas, right? So for these interesting families of things, for the elementary symmetric, we actually got polynomial quadratic size sigma pi sigma formulas, but for the others, we got significant improvements, but not all the way down to polynomial. Okay, and there's no reason to believe that we can get all the way down to polynomial. In fact, for the permanent, we believe that we can't probably do much better than this 2 to the n. Okay, so we do expect that at least some of these constructions we have are tight. Yeah, but unfortunately, we haven't been able to prove any of that yet. So the best lower bound we had for sigma pi sigma before our work was something like cubic. This is a work of Kayal, Saha, and Tavanas from about 5 years ago. And so what our result does is, at a technical level, is that it shows that this final upper bound here for iterated matrix multiplication is actually tight. Okay, so what we show is that any sigma pi sigma formula for the iterated matrix multiplication polynomial has size at least n to the square root d. Okay, that's kind of the technical statement of our result. Unfortunately, there are a couple of caveats. So as Avi mentioned already, in the case of the determinant upper bound, we have a similar thing for the lower bound. Again, we have characteristic 0, this condition. But we also have this other condition where we require the degree of the polynomial to be less than log n. Okay, so we don't really get things for arbitrarily large degrees. We get something for larger degrees, but not n to the root d. Okay, so this is the statement of result. And so we are not therefore able to get something like an exponential lower bound. The best lower bound we can get is n to the square root log n, which is super polynomial, but not as good as n to the square root d for general. Okay, so that's a statement of result. And so this is the lower bound for IMM, and so this is kind of our main technical theorem. And by standard techniques, we can actually transfer this lower bound also to other polynomials like the determinant and the permanent. Okay, so just kind of plugging in our IMM lower bound into standard reductions, what we are able to show is that any sigma pi sigma formula for these polynomials must have size n to the root log n. So this is the lower bound we get in general as a super polynomial function. Okay.
So if you could handle d up to n, then you would get the correct bound?
Right, absolutely. So if you could take d up to n, then we would get the correct bound for the determinant. Yeah. Actually, I would have to think a little bit about that. I'm not 100% sure. You would get, of course, closer to the correct bound. You would get n to the something, but it's not clear to me that you would get n to the root n. So I'm not sure though. Yeah, you'd get closer definitely, but it's not clear that you would get exactly the right bound. Yeah, but the determinant is a polynomial where the degree and the number of variables are somehow linked. So it's not so clear to me that you would get exactly the right bound. Okay, so fantastic. So this is sort of part of my motivation for this problem. And now let me explain sort of the other part, which is the connection to this important question called the VP versus VNP question. Right. So I assume that many people in the audience are already familiar with the P versus NP question, which is this famous question regarding if certain a very interesting class of combinatorial optimization problems all have efficient polynomial time algorithms. So the VP versus VNP question is kind of an algebraic analog of the same question. Okay, so it's so we look at not all computational problems, but certain algebraically defined computational problems, and we don't look at all general algorithms for such problems, but certain algebraically defined algorithms. And we ask if every problem from this class has an algebraic algorithm from the corresponding algorithm class. So that's the setup. So let me sort of describe it. So our problems are all defined by sequences of polynomials, right? We've already seen examples of these, but you could have here an arbitrary sequence of polynomials. And given a sequence of polynomials, you have the following computational problem. And the problem is just to evaluate these polynomials, right? So you're given as input some point A in some n-dimensional vector space, and the desired output is the value of the nth polynomial at this point. Okay, so that's the computational problem defined by sequence of polynomials. And many natural computational questions that we care about are naturally described this way. Okay, so the determinant, for instance, of course, is extremely natural as a computational object. You want to solve the determinant if you want to do linear programming or solve linear equations or a whole lot of things. The permanent, again, is extremely important. It comes up in all sorts of combinatorial counting questions. for instance. And iterated matrix multiplication has, of course, many graph theoretic interpretations. It is complete for various complexity classes, etc. So all of these are naturally defined as polynomials, but also kind of natural computational questions in their own right. Okay, so there are many questions that are captured by this in this general framework, right? And now when you're given a question of this form, right, your question is you have a family of polynomials. Now you want to evaluate these polynomials. What kind of algorithms could you look at? Well, in principle, your algorithms could do anything, but natural algorithms for such problems would sort of involve the algebraic operations of the underlying domain, right? So in particular, since polynomials are defined using additions and multiplications, it's natural to look at algorithms that also use just additions and multiplications in order to evaluate the polynomial. And this is essentially what an algebraic circuit or the model of computation we are interested in is. Okay, so let me just define this. So what's an algebraic circuit? So you start off with your underlying variables at the bottom here, x1 through xn. And so these are sort of these represent your input. And starting with your input, what you can do is you can iteratively apply some simple operations. And what are the simple operations? You can take linear combinations of elements that you already have. You can multiply elements that you already have, and you can apply these operations iteratively one on top of the other. Okay, so for instance, here we take some linear combination of x1 and x2, take some linear combination of xn minus 1 and xn, multiply some things together, maybe add some of those, etc., etc. So iteratively, you compute more and more complicated polynomials in your underlying variable set until finally you reach some sort of output node or output gate, which is supposed to evaluate the polynomial you're interested in evaluating. Okay, so this gives you a certain kind of algorithm for solving this kind of computational problem, right? So there's an algorithm that uses just additions and multiplications and solves your computational problem. Of course, in principle, a general algorithm doesn't have to look like this, right? A general algorithm doesn't have to apply just algebraic operations. It could use something about the bit representation of the inputs, etc., etc. So we're not looking at algorithms of that form. We look at this restricted class of algorithms for evaluating polynomials. Okay, so this is what an algebraic circuit is. And an algebraic, so just like for formulas, we have a notion of size. And here again, the size is just the number of edges in this graph or the number of wires in this circuit. Okay, so that sort of captures the efficiency of the algebraic circuit. Okay, and you can see just by this picture here that this an algebraic circuit is a more general object than the algebraic formulas that we defined some time ago, because algebraic formulas were just, well, they look like this, except that the underlying graph was a tree. Okay, so these circuits are sort of more generalized expressions, if you will. Yeah, you can think of them as generalizations of algebraic expressions. Okay, so generalized algebraic expressions. And the class of polynomials that define a computational problem, we say that that's in VP. Okay, we say that it's in the algebraic version of P if the nth polynomial in the polynomial sequence has a circuit of size polynomial in it. Okay, so that's the definition of VP, so or the version of P in the algebraic world. Okay, so I've defined algebraic P. Maybe I should also define algebraic NP, so I can talk about the VP versus VNP question. So what's algebraic NP? So NP is a little bit of a mouthful to define, so I'm not going to give you the formal definition here, but I'll give you more kind of an operational definition, which is, I think, enough for most purposes. So VNP is sort of a large class of interesting polynomials that we want to be able to solve in this way. Okay, so we spoke some time ago about explicit polynomials. Essentially, any polynomial that probably popped into your head at the time was a polynomial in VNP. Okay, so that's kind of the intuition. So more formally, VNP is defined to be a class of polynomials that contains all these interesting classes that I'll tell you about. So in particular, it contains VP, right? So any polynomial that you can produce an algebraic circuit for, we think of as explicit enough to be in VNP. So it contains VP. Okay. It also contains a large class of polynomials that kind of express natural counting problems. So very often the kinds of polynomials that we look at come from some natural counting computational problems or the other, for instance, like counting cliques in graphs or counting Hamiltonian cycles in graphs or counting matchings in graphs, etc., etc. So any polynomial that's kind of comes from a natural counting problem defined this way is probably in VNP. Okay. And finally, and this is what I meant by an operational definition of VNP, is that any polynomial where you can easily describe the coefficients of the polynomial is in VNP. Okay, so as an example, consider something like the determinant, right? So the determinant, it's not immediately easily clear that it has a small expression of any kind, but it is very easy to describe the coefficients of the determinant, right? So given a monomial, you can kind of say, oh, what is the coefficient of this monomial in the determinant? Oh, if the monomial doesn't look like this, the coefficient is 0. The monomial looks like this, it's either +1 or -1, depending on the sign of some permutation. Okay, so any polynomial where you have an efficient algorithm that can compute the coefficients of that polynomial is a polynomial in VNP. Okay, so VNP is sort of a nice class of interesting polynomials that contains all such polynomials, right? And the big question of this area is whether all polynomials that are explicit in this way are also efficiently computable. Okay, is VP equal to VNP? Is every polynomial which has efficiently computable coefficients, is it also efficiently computable in the sense of having a small algebraic circuit? Okay, and the answer is conjectured to be no. Okay, and it's a pretty strong conjecture for the reason that if you believe that P is not equal to NP, then it's very likely that VP is not equal to VNP. Okay, so what Burgesser showed was that if you prove that P is not equal to NP or some variant of it in the non-uniform world, then that in particular implies that VP is not equal to VNP. Okay, so since most of us believe that P is not equal to NP, we also believe that VP is not equal to VNP. But what this also means is that VP not equal to VNP is sort of like can be seen as an easier version, an easier cousin of P not equal to NP, and maybe even a stepping stone to this more general question. Okay, so great. So let's see a few examples, but maybe I've been sort of rocketing along for a while, so maybe it's a time to just pause and see if there are any questions. Any questions? Comments? I think. Okay, fantastic. All right. So okay, so let me do a few examples here. Let's look at some of the polynomials we've already seen. So for instance, the elementary symmetric polynomials, well, we already showed that they have formulas of polynomial size, and formulas are special cases of circuits. So in particular, we showed that the elementary symmetric polynomials are in VP. Okay. What about iterated matrix multiplication? Well, iterated matrix multiplication, it's pretty clear that you can multiply two matrices efficiently, or at least in polynomial time. And the standard matrix multiplication algorithm can definitely be written down as an algebraic circuit, right? And this implies that iterated matrix multiplication is in VP. Okay. A more interesting example is the determinant, right? So the determinant it's not completely clear how to write down an algebraic circuit for it. The standard way to compute the determinant efficiently is via Gaussian elimination. Gaussian elimination does not immediately yield an algebraic circuit for a couple of reasons. For one, the typical use of Gaussian elimination requires you to check if certain entries are 0 or not, right? And this is not really an algebraic operation. Checking if something is 0 or not is not really an algebraic operation. And for a second, you also use divisions in Gaussian elimination. And the way we define algebraic circuits is just additions and multiplications. Yeah, but nevertheless, with a little bit of work, you can actually overcome both of these and come up with show that the determinant does have polynomial-sized algebraic circuits. So it is in fact in VP. There are also division-free ways of computing the determinant, like Leverrier's method, for instance, and you can use those as well to show that the determinant has polynomial-sized algebraic circuits. Okay, so all of these examples are in VP. These are all interesting examples in VP. Okay, an interesting example which is not known to be in VP and not suspected to be in VP is the permanent. Okay, so the permanent, just to recall, was the determinant polynomial, but without the sign term. So definitely it's one of those polynomials where you can compute the coefficients of the polynomial very, very efficiently, right? So it's definitely in VNP, okay, but it's not known to be in VP. And in fact, the story of the permanent is intimately tied to the VP versus VNP question. Okay, so when people started, so the study of this question was initiated by Valiant. And in fact, he started it as a way of kind of trying to understand the complexity of the permanent. Okay, and in the course of defining these complexity classes, Valiant in particular proved this amazing result, a kind of a completeness result for the permanent. What he was able to show, Valiant, is in the spirit of the Cook-Levin theorem in standard Boolean complexity, Valiant was able to show that the permanent is VNP complete. In other words, it's the hardest polynomial in VNP. Okay, so what that formally means is the following. Take any polynomial sequence in VNP, in this very large class of polynomials, where given any such polynomial sequence, the nth polynomial in this sequence, Pn, can be written as a linear substitution of a not much larger permanent. Yeah. So what does that mean? So for the nth polynomial Pn, there is an m which is not much larger than n, such that Pn can be obtained by starting with the m by m permanent and replacing the entries of that permanent by linear functions in the variables of Pn. Okay. So in that sense, the Pn can be obtained as a sort of linear substitution of the permanent. And what that means is that if the permanent has polynomial-sized algebraic circuits, by applying this linear substitution to those polynomial-sized algebraic circuits, you could also get a polynomial-sized algebraic circuits for Pn. Okay. So in other words, if Vp is not equal to Vnp, then it must be the case that the permanent does not have polynomial-sized algebraic circuits. Okay. So this very general question of whether two classes of polynomial sequences are the same reduces to this one very concrete question of whether the permanent has polynomial-sized algebraic circuits or not. Yeah, which is, I think, an amazing result. Okay, so that's Valiant's theorem.
Even more striking because determinant is complete for Vp. It's really the question of the relation between permanent and determinant.
Right. Yeah. So Avi says, yeah, there's an analogous result for the determinant, but the determinant is close to complete for Vp. Right. So yeah. So this question can be phrased even more concretely as asking whether the permanent can be obtained as a linear substitution of the determinant, which is of a determinant which is not much larger than n. Right. So yeah. So that's that makes the question even more concrete. And if I remember right, that is the language in which Valiant originally asked the question. Okay, so fantastic. So that's the Vp versus Vnp question. So what we'd like to do is to show that Vp is not equal to Vnp. So that's equivalent to showing that the permanent does not have polynomial-sized algebraic circuits. Okay, and so how far are we along on this path, right? So we want to show that the permanent or some explicitly defined polynomial in Vnp does not have polynomial-sized algebraic circuits. So what do we know in this matter? Well, for general circuits, it turns out we don't know much. Right. So this is the best lower bound that we know, and this is a lower bound of Bauer and Strassen from the early 80s, who showed that any algebraic circuit, so they showed that for some explicitly defined polynomial, any algebraic circuit for that polynomial must have size at least n log d. Okay, so since d is at most n, this gives you at most an n log n lower bound for some explicitly defined polynomial, but not much more. Okay. Around the same time, again in the early to mid 80s, a result of Kaler-Coty gives slightly stronger lower bounds, but in the setting of algebraic formulas, right? So circuits are more general than formulas. So formula lower bounds are slightly weaker notion, but for formulas, we actually know lower bounds which are nearly quadratic, right? But not better than quadratic since then. Okay, so in general, we haven't sort of come very far along the road to proving Vp is not equal to Vnp, despite it being an easier version of P versus Np. But what we have been able to do, despite not being able to prove lower bounds for these general models of computation, is to be able to prove a slew of lower bounds for slightly weaker notions, where weaker is defined in terms of some sort of syntactic restriction, further syntactic restriction. So I'm not going to be able to survey this vast area of research that's gone on in the last 20 or 30 years, but I want to give you just a couple of pointers. Okay, so one family of such results pertains to this family of circuits called multilinear circuits. Okay, so what's a multilinear circuit? Well, a multilinear polynomial is one in which each variable has degree at most 1. Right, so you're never multiplying a variable with itself. So you have no monomials that contain x1 square or x2 cubed or things of that sort. Okay, that's a multilinear polynomial. And so all the polynomials we've defined so far are multilinear. Okay, and a multilinear circuit is a circuit which is restricted in the sense that every gate is forced to compute a multilinear polynomial. So it's not allowed to multiply variables with themselves. Okay, and so these are definitely restricted kinds of circuits. But under this restriction, we have a variety of lower bounds. Okay, and this sort of started off with this work of Avi and Noam Nissan that I spoke about some time ago, and continued with some amazing results of Raz and Yehudev, and there are many others that I haven't mentioned here. But what we know as a result of these, all these works, is that we have superpolynomial formula lower bounds, so much stronger than what we know for general formulas, and also exponential constant depth circuit lower bounds. Okay, so we have very strong lower bounds under this restriction of multilinearity, and that's a kind of a whole research area in itself. And it turns out that the lower bound that we prove builds a lot on some of these results. Okay, so we essentially use the same technique, slightly modified. All right, so that's multilinear circuits. We also have lower bounds, as I said some time ago, under restrictions such as homogeneity. Right, so if you have a homogeneous polynomial of degree d and you force the intermediate terms inside the formula to also have degree at most d, then you get this homogeneous kinds of formulas. And under this kind of restriction, again, we have lower bounds of various kinds. Okay, so again, this is result of Nissan-Wigderson and then follow-up works of Kayal, Gupta et al., etc. So we have many results here as well. Okay, so but under these kinds of syntactic restrictions, we do have stronger lower bounds. But as I said, beyond, if you throw away these kinds of restrictions, the best lower bounds we knew was n square, and for formulas, and even for sigma pi sigma formulas, it was only cubic. Okay, before our result. All right, so that's sort of the context behind our work and the VP versus VNP question. But now let me just sort of relate our final theorem to the VP versus VNP world, kind of close the loop here. Okay, so what have we done, right? So as I told you, we get lower bounds for constant depth circuits. So where does that fit in this whole picture? Well, this is the kind of standard kind of diagram that complexity theorists love to draw, right? So you have the outermost circle here is VNP, and the circle inside that is VP. And what we'd really like to show is that these two circles are ellipses are different. We are not quite able to do that, but what we are able to do is we are able to prove lower bounds or prove a separation between the VP class and the class of constant depth circles, which is a kind of a sub-ellipse there. Okay, and more specifically, we show that these polynomials, determinant and IMM, are both sitting outside that smaller ellipse. Okay, so that's the kind of thing that we've been able to do. And as Avi mentioned some time ago already, the reason this result is kind of was sort of expected is that such results were known for Boolean complexity. Yeah, and Boolean complexity is essentially general algorithms, not necessarily algebraic algorithms. And our intuition, building on what Burgesser has already shown, is that algebraic complexity is sort of algebraic complexity lower bounds are sort of easier than Boolean complexity lower bounds. So though this theorem doesn't work in the constant depth setting, so our intuition sort of told us that algebraic constant depth circuit lower bounds should be achievable. And we've not been able to get this until now, and it's something that we now have. Okay, so that's a nice thing. Okay, so that's sort of some of the context behind our result and how it relates to VP versus VNP. There's another kind of nice connection, which is that which is this kind of notion of depth reduction, which is really an amazing result about algebraic circuits, which tells us that strong enough constant depth lower bounds actually imply general circuit lower bounds. So in fact, the kinds of results that we are proving, they seem to be quite restrictive because they only apply to this very small class of circuits seemingly. But what we know is that strong enough results, even for these very restricted kinds of circuits, can in fact have the potential to separate VP from VNP. Okay, so what does that mean? Well, in particular, we have results of the following form. So let me just flash this result here. So there are many results like this, but I want to tell you about this particular one because this is the one that's mostly closely related to our work. So a result of Gupta et al. Shows that when you have a sequence of polynomials in VP of degree at most d, this sequence of polynomials also has sigma pi sigma formulas, yeah, the kind of restricted formulas that we prove lower bounds for, of size n to the square root d. Okay, so I don't want you to worry about these parameters too much, but the main thing to note is that this n to the square root d is much smaller than the trivial n to the d. Okay, so in particular, you can always start with a polynomial size large depth circuit and kind of squish it down to a sigma pi sigma formula. This process of kind of squeezing it down in terms of depth blows up the size of the representation, but still keeps the size of the representation non-trivial. Okay, so it's still much smaller than n to the d. It's like n to the root d. Okay, so which is interesting, right? Because what this means is that a strong enough lower bound for sigma pi sigma formulas, specifically a lower bound of more than n to the root d for your favorite polynomial, would imply that that polynomial is not in VP, and that would imply perhaps that VP is not equal to VNP. Okay, and this is a very much a feasible way of separating VP from VNP, for instance, for the permanent, because we don't expect the permanent to have sigma pi sigma formulas of this sort. Okay, so if you could prove such a thing for the permanent, then you would be able to separate VP from VNP. Okay, so which is an amazing thing. So this kind of thing is not known for Boolean complexity, but what it implies is that in the algebraic world, proving a lower bound for this very restrictive model of computation already implies a general circuit lower bound. Yeah, which is a really cool thing.
It's not that it's not known for Boolean complexity. It's not true for Boolean complexity.
It's not. Yeah. It's.
You cannot take a, I mean, you have a polynomial circuit for majority, but you cannot push it down.
That's true. Right. Yeah. But I guess it's also a question of parameters, right? Because the lower bounds we have for majority, well, there's something, but maybe you could push it down to something a little bit more than that.
You have exponential lower bound for majority if you talk about depth width.
That's right. Right.
You want more than,
Yeah.
it's degree, I think what you're saying, you just 2 to the root and lower bound. So that's
right.
what, okay.
Yeah, it's not completely clear, but I believe what you're saying. Yeah, so it's not known to be true. It's unlikely to be true, perhaps.
Right, but 2 to the root n there is tight, happens to be tight. So unlike here.
Right. That's right. That's right. Right. So it's feasible that we can prove strong enough lower bounds for sigma pi sigma and actually get lower bounds for VP. Okay. And what do we get from our result? Right. We actually get lower bounds of form n to the root d. Right. So I told you what the lower bounds we get for the iterative matrix multiplication polynomial. D is small, but that's irrelevant for this result. We get lower bounds of n to the root d. So could we push beyond n to the root d and prove lower bounds for VP? Well, not for this particular polynomial, because this polynomial happens to be in VP. So obviously not for this polynomial, but it seems like there is some sort of progress, right? I mean, previously, so this seems like some sort of approach to prove lower bounds separations between VP versus VNP, but previously we didn't even have super polynomial lower bounds for sigma by sigma. Now, at least we have n to the root d lower bounds, but maybe we're still at the place where n to the root d versus super polynomial and n to the root d is the same as n versus super polynomial and n for general circuits. So it's not 100% clear, but it seems like some sort of progress has been made. Okay, so yeah, I don't want to say too much about this, but yeah, this is it's kind of nice progress towards VP versus VNP from this kind of point of view. Okay, a similar situation is also true for homogeneous sigma pi circuits. Again, proving super polynomial n to the root d would imply separation between VP and VNP, but we have n to the root d, but not more. Okay, so
could it be that if you optimize your constants and you get some better polynomial lower bound for formulas this way?
That's a good question. I've never tried it. I doubt it. Maybe we're very sloppy with constants, but our constants are quite bad, I think, because you would have to optimize constants in both the results, right? Yeah, it could be, but yeah, I don't know. I've never tried it. So yeah. Could be.
Certainly tried it in the homogeneous sigma pi, and of course the constants don't
okay.
go in the reverse order. So.
Okay, I see. Yeah, right. Yeah. So I haven't tried, but yeah, it's definitely worth trying. I don't know.
Well, in principle, yeah. If you get large enough arbitrary constant lower bound before the square root d, then you did it.
Right. Yeah, you could. It could even be just you could get n to the 1.5. That would still be interesting. And I don't know if we just can't give that. Yeah, but I should say that the way that this our lower bound proof method is sort of optimized for IMM. So I don't know in that term, in those terms, whether you can really get, super linear lower bounds, or I don't know what you would expect here. But yeah, so that's something to definitely think about. Okay, so great. So how much time do I have left, Avi?
10 minutes roughly.
Oh, okay, fantastic. So that's great. So that means that I can at least tell you about the polynomial identity testing application, which is great news. So I want to kind of conclude by telling you an application of our lower bound result to a completely different, or at least seemingly different kind of problem. And this is also a famous problem from the area. It's the problem of polynomial identity testing. Okay, so what's polynomial identity testing? Well, what's a polynomial identity? This is a polynomial identity, for instance, right? So it's these kind of magical polynomial identities, these magical identities that crop up in different parts of mathematics. I think this identity expresses something about quaternions or something. So a polynomial identity is just a polynomial p equals a polynomial q, right? And or equivalently, you can express it as p minus q equal to 0. And the polynomial identity testing problem is given a candidate polynomial identity. Check whether it's actually an identity or not. Okay, so that's a polynomial identity testing problem. More formally, you're given a polynomial p x1 to xn. And how's this polynomial given? It's given not as a list of monomials, but in encoded form as a circuit. Okay, and the question is P an identity? Is P identically 0? So that's the polynomial identity testing question. Okay, and so how would you solve this as an algorithmic problem? So given a polynomial as a circuit, how would you check if it's identically 0? Well, a natural thing to do is to kind of expand it out. So if you're given two expressions like this, maybe expand them both out and check coefficient by coefficient if they match up. And if they do, that's an identity. If not, it's not, right? And there's an obvious drawback to this algorithm. It takes a lot of time, right? So the number of coefficients is again something like n to the d, and you don't want to take so long in order to check if this is actually an identity. You want, in fact, a polynomial time algorithm, a very efficient algorithm. Okay, so that's the question. So how do you go about coming up with such an algorithm? Well, there's an obvious strategy if you sort of allow yourself randomized algorithms. Okay, so what's a randomized algorithm for this problem? So it's very simple. So if you have a non-zero polynomial, right, your input polynomial is non-zero, then the zeros of the polynomial form sort of a hypersurface in your vector space, right? And so if you pick a random point in your vector space, very unlikely to fall on this hypersurface. So a natural kind of candidate algorithm is just choose a random point in your vector space, evaluate the polynomial at this point, and if it's non-zero, say it's not an identity. If it's 0, say it's an identity. Okay, so that's a kind of a natural algorithm that you might think of. And in order to kind of check that this algorithm works, you need a lemma that tells you that a non-zero polynomial doesn't vanish too often. And thankfully, we do have lemmas of this form. So here's the standard lemma that we use all the time in this area. So it's been discovered by many people at many different points of time. And so what this polynomial identity lemma actually says is that if you pick a random point in a large enough discrete grid, right? So think of S as a finite subset of the field. Take a random point in S to the n. The probability that this point lands up in the 0 set of this polynomial P is at most the degree of P, which is hopefully a small number, divided by the size of S. Okay, so most points in this high dimensional discrete set do not lie on this hypersurface. So in particular, if you design your algorithm this way, pick a random, fix a subset of the field of size slightly more than the degree of P, choose a random point from this discrete set and test if P of A equal to 0, then this algorithm is probably going to be able to tell if your polynomial is 0 or non-zero with high probability, correctly with high probability, right? So if P is 0, of course, any point you pick will be a 0 of the polynomial. If P is non-zero, then this lemma tells you that a random point from this grid is not going to lie on the 0 set of P with high probability. Okay, so does this make sense? The randomized algorithm, the problem, etc. Okay, so great. So this gives us a simple randomized algorithm. And the big question in this thing is, can we get efficient non-randomized or deterministic algorithms for this problem? Okay, can we be at the same time efficient, like this algorithm is efficient? It's definitely very efficient, but at the same time, not use any random bits and kind of give the right answer all the time. Okay, and that's the big question. And now, what does this have to do with lower bounds? Yeah, this is completely not clear. What does this have to do with the kind of VP versus BNP question and all the other stuff that we were talking about some time ago? It turns out that there's a close connection. So I'm stating here a theorem of Cabinets and Impagliazzo, who showed that if you can show VP not equal to VNP, for instance, if you can show explicit lower bounds against algebraic circuits, then in fact you can solve this problem deterministically in better than exponential time. Okay, so you can solve this algorithm deterministically, not all the way down in polynomial time, but much better than exponential time. Yeah, and this sub-exponential can in fact be brought close to polynomial if you assume not just a super polynomial lower bound against algebraic circuits, but stronger lower bounds. Okay, so there's a sort of a trade-off between the kind of lower bounds you have and the efficiency you get in deterministic algorithms for this class. Okay, and this connection itself is kind of builds on a long line of work in this area, and it generally goes by the name of hardness versus randomness. And this is a whole story in itself, and I won't say much about this. But just to say that Cabinets Impagliazzo itself is sort of follows on a long line of work, and there's been much more work in this sense. Okay, so in particular, what we would like to do is to use our lower bounds to achieve polynomial identity testing algorithms of some sort. And Cabinets Impagliazzo doesn't give it, because what Cabinets Impagliazzo needs is lower bounds, not just for constant depth algebraic circuits, but for general algebraic circuits. And that gives us deterministic sub-exponential time algorithms for PIT in general. But it turns out that some of the work following Cabinets-Impagliazzo is applicable in our set. Okay, and so this is exactly the theorem that we need here. So this is actually a recent result of Chow, Kumar, and Solomon. And what they show is this amazing result that is perfect for our application. And so what they show is the following. They show that if you have, instead of lower bounds against VP, but if you have lower bounds against constant depth circuits, okay, and moreover, the polynomials for which you prove these lower bounds are low degree polynomials, right? Then this implies that you get sub-exponential time PIT for constant depth circuits. Okay, so just like Cabinets-Impagliazzo says, lower bounds for VP implies PIT for circuits given for polynomials given as general circuits. These guys give the same kind of result, but for constant depth circuits, with the additional proviso that your lower bound is proved for a low degree polynomial. Okay, and the reason this is perfect for us is that I told you that our lower bounds only apply to low degree polynomials. So it's sort of exactly what we need. So as a corollary, what we get is that we get sub-exponential time polynomial identity testing algorithms for constant depth circuits. Yeah, and this is actually a kind of a nice result because so previously we didn't have sub-exponential time PIT algorithms even for sigma pi sigma circuits. So this is kind of a new result which was not known, though many other kinds of PIT algorithms of higher efficiency were known. Okay, so I think that's about all I had to say. I have something about the actual proof, but I think I'm out of time, so let me just skip that and skip over to the summary. Okay, so what did we do, right? So I just told you about superpolynomial lower bounds against this kind of model of algebraic computation, constitutive algebraic formulas. This is new in the sense that lower bounds are given for the sigma pi sigma case unknown. So it's kind of nice in that way. And the great thing about this research area in general is that this kind of very concrete sigma pi sigma lower bound has the potential to prove something like VP not equal to VP, which would really be an amazing result. Okay, so for those of you who have not seen this before, I invite you to kind of come and think about it. It's a place where very concrete, beautifully defined combinatorial algebraic questions actually imply these amazing results about computation. Okay, so some open directions. What we can, so what something we'd like to do regarding our lower bound is, one thing is we'd like to do is something that Yuval asked already about. Our lower bounds hold a constant depth and slightly growing depths, but we would actually like to hold make our lower bounds hold for arbitrary depths, ideally for formulas at least, but we don't know how to do that. And there are also some sort of technical questions. I told you our lower bounds only hold for small degrees, so they only give us super polynomial lower bounds, not exponential lower bounds. We'd like to get exponential lower bounds. Our lower bounds hold to a zero characteristic, but it feels like we use zero characteristic in a very restricted way. So it feels like we should be able to get something more positive characteristic. And we don't know that yet. And so that's another nice kind of open direction. Okay, so that's it. Let me stop there. Thank you.
Okay, questions to Srikanth? Audience, Zoom.
So actually, for the Ben-Or construction, is something better than n squared known, or what? Or is it known to be tight?
It's known to Amir Spilka and I prove that it's tight. There is an n squared lower bound also. It's yeah, it's some work.
Right. Absolutely. Though I don't know if we know the correct lower bound for every n and d. So if you kind of vary n and d, I'm not sure we know the right thing. Yeah, but for
there are n and d, but for linear d, it's n squared.
Okay.
Right, and there is a lower bound for every d, but like Srikanth said, it's not necessarily matching. I mean, the upper bound is n squared for every d. There's no way Ben-Or can say using the fact that. Right. I mean, there's more things in this paper with Spilka, and you know, sometimes you can't say for smaller things. Anyway, let me not go into this. More questions? Okay, Srikanth. So thanks a lot, and tomorrow we'll see the proof. All right.
Thanks a lot.